Okay, now we're looking at this function y equals 2x squared over x squared minus 1. Like we were doing before, let's start out by determining the domain. Now on a function like this, the domain is particular. We have to check where the denominator is equal to 0. So x squared minus 1, where is that equal to 0? Well, if we solve for x, say x squared equals 1, and take the square root plus or minus, we'll have x is equal to negative 1 and x is equal to positive 1. And so both of those numbers from the denominator are not in the domain. The domain would look like negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. So all the numbers except for those two would be in the domain. Okay, let's go ahead and find the x and y intercepts. So like we did before, to find the x-intercept, we'll set y equal to 0. Okay, we have to solve for x. Now technically that denominator is just going to cancel out if we multiply both sides by the denominator. It's just going to go away. So really we'll just have 2x squared is equal to 0, which tells us x is equal to 0. So that's again now our x-intercept. We should be able to find the same in the y-intercept. We plug in 0 for x. In this case, it should work out to be the same. 0 divided by negative 1, so that would be 0. So still the origin 0, 0 for our y-intercept. Alright, so now we know a little bit more about the function. Let's go into the asymptotes. Okay, so this kind of will call back to some of the things from college algebra. We talk about the vertical asymptotes, which I'm going to abbreviate VA. And so the vertical asymptotes, basically all I'm going to do is take the denominator and figure out where the denominator is equal to 0, which we just did for domain. We had solved for x and we got negative 1 and x is equal to positive 1. And so those two numbers are also referring to the vertical asymptotes. X equals negative 1, x equals positive 1, both refer to the vertical lines. Now for horizontal asymptotes, I'm going to use the shortcut way to work on that part. Basically, in this case, since the powers of x on top and bottom are identical, what I'm going to do is just divide the leading coefficients. So divide 2 by 1. So y equals 2 divided by 1, or y equals just 2, would be the equation of the horizontal line, which goes for the horizontal asymptote. Now, to talk about the last one, the slant asymptotes, which I'm abbreviating here SA later, but basically we're not going to have any slant asymptotes if there's a horizontal asymptote already. So those go now to show us what our asymptotes are. Let's go then into doing the first derivative test to figure out where it's increasing and where it's decreasing. Okie doke. So, well, we've got to find the derivative. So let's go to the function that we had up above. How do we find the derivative of a function like this? Indeed, this is going to involve using the quotient rule in order to do the derivative. So let's go through the quotient rule. It goes low, d high, minus high, d low, all over the square of what's below. Okay, so now this is how it's going to work out with the quotient rule. We got to clean it up though a little bit. Looks like we're going to get here 4x cubed minus 4x cubed all over x squared minus 1 all squared. Well, thankfully, the 4x cubed will go ahead and reduce, go away. We'll just have negative 4x in the numerator. So, in order to use our first derivative, this is not something we had to do in the last one. We have to solve it for 0. So set the first derivative equal to 0, but also we have to determine where the first derivative does not exist. There's two things we're going to have to worry about here for our critical numbers. That's what this is all about, the critical numbers. So setting it equal to 0 is not too bad. We just set the whole first derivative to 0. Basically the denominator will cancel in situations like this, so really we're just going to consider the numerator to solve for x, which in this case would just give us x equals to 0. Now to figure out where it does not exist, it's all going to come back to the denominator. Where is the denominator equal to 0? Well, basically if we take the whole denominator, set it equal to 0, it's going to come right back around to just x minus 1 by itself equal to 0. The power of 2 makes no difference here. So we've already considered the solutions of negative 1 and positive 1 for x from the very beginning, for x squared minus 1 equal to 0. So those are also included here for our critical numbers as well. So we have 3 critical values to take a look at for this one. So we have lots of intervals to discuss and test values to choose. For this, I'll choose fairly straightforward numbers: negative 2, negative 1/2, positive 1/2, and 2. Okay, and those are going to be the numbers I'll now use for this part. Okay, let me go through all these intervals we're dealing with. So unfortunately we do have 4 intervals to look at. So we'll have to list them all out here, along with our test values and all that stuff. Okay, so let's see, got our test values. We'll be plugging these in like we've had so far for the first derivative. So again, our first derivative being negative 4x divided by x squared minus 1 all squared. Now if I start off with negative 2, we have negative 4 times negative 2 all over negative 2 squared minus 1 all squared. It's going to look something like positive 8 divided by 9. So we see that we're getting a positive number, and we know we have to be increasing. Now we could do this for all the various numbers, plugging in negative 1/2, plugging in all the other numbers. Now if we do plug in negative 1/2, just thinking about the numbers here, I'm plugging in a negative on top, a negative squared, minus 1 squared underneath. So basically we're going to get a positive divided by a positive. It's all going to be positive still. But you can always double check by just plugging in negative 1/2 and doing the calculation. For positive 1/2, now we're plugging in a positive number. Positive squared minus 1 all squared. Basically, since the denominator is squared, denominator should always turn to be a positive. But here on top we'll get a negative number, so this will turn into a negative decreasing. If we plug in 2, it's been positive underneath but a negative on top, so it's going to be negative decreasing. Okay, so now we know increasing, increasing, decreasing, decreasing. There are not too many alterations here. So we'll say increasing from negative infinity to 0, decreasing from 0 to infinity. Okay. We also know about an absolute local maximum. Here at 0, since it goes up and comes back down, that's a local maximum. So a local maximum located at x equal to 0, and if we plug that in and figure out what y is equal to, it's also 0. So 0, 0 is a local max. And so there's nothing else to discuss here. We just have our increasing, decreasing, and one local max point to worry about. Okay, now we're continuing on into the final step in this process, and that's to determine concavity. And the way we did that again is by using the second derivative. Well, here's our first derivative. We have to take the derivative of this in order to get the second derivative. A little bit tricky, but we'll go ahead and handle it here. To find y double prime, this is going to be quotient rule yet again, but we also have to mix in the chain rule a little bit from the denominator, unfortunately. So let's see, we do low, d high, g high is only -4, so not too bad to get started, minus high times d low. Now to take the derivative of the bottom part, it's going to look like 2 x squared minus 1 times 2x. That's the chain rule from the denominator. All over the square of what's below. So if we take what's below, square it, it's now going to be to the 4th power instead. Okay, so let's do our best to try to simplify this down and use it to help us figure out the concavity. Let's make this look like -4 x squared minus 1 squared plus 16 x squared minus 1. Okay, looking at this, I see some GCF stuff I can deal with. Specifically, I notice that there is a 4 in common, so why don't we go ahead and pull that 4 out from both. We can also move around an x squared minus 1. And so if I take that away, that's going to leave me with just x squared. To make this a little more convenient, let's make that a -4. I'm going to take that -4 that's in the front. If I do that, then moving the factors around, we'll have an x squared minus 1 here. Fortunately, we'll have to change this to a negative since I factored out a -4. -4 x squared all over x squared minus 1 to the 4th. Okay, combining like terms and doing all that to simplify, we have -4 x squared minus 1 times -3x squared minus 1 all over x squared minus 1 raised to the 4th. Now, a cool thing is this x squared minus 1 can be reduced with 1 from the denominator, so that's a little nice simplification here. So we get -4, -3x squared minus 1 all over x squared minus 1 raised to the 3rd power. Okay, now we'll basically do with the second derivative what we did with the first derivative. We got to solve it equal to 0. Okay, number 1. And we also need to check where the second derivative does not exist. Okay, for setting it equal to 0, why don't we just take a shortcut and just look at the numerator, since that's the only thing we really have to worry about here. The denominator, we'll check that a little bit later. Now if we set this equal to 0, solve for x, Really, we just have to set this factor equal to 0, negative 3x squared minus 1 equal to 0. So let's see, we'll have x squared is equal to 1/3, or sorry, I should say negative 1/3, because if we go through the process of solving, we have to add over the 1. Negative 3x squared equals 1, so x squared is equal to negative 1/3. Which just kind of led us down a wild goose chase, because if we do try to solve for x, we're looking at now imaginary numbers. So since this has an imaginary solution, because of the square root of a negative number, we're just not even going to look at any particular solutions here. So this doesn't yield us anything in particular. So we're done with this part. We will go over here and check where it does not exist though, however. That's all going to come back down to, again, where the denominator is equal to 0. So that denominator, x squared minus 1 cubed to the 0 equal to 0. But that still just really comes down to just the x squared minus 1. No use for the power of 3, which we've been looking at already as the negative 1 and the positive 1 solutions. So those are the only two numbers we're going to have to deal with to check along the number line. So negative 1, positive 1. Test values I'm going to use are negative 2, 0, and 2. Thankfully, fairly straightforward numbers to work with in this case. Negative infinity to negative 1, negative 1 to 1, and 1 to infinity are the three areas we're checking. And we'll be checking now with the second derivative, y double prime, from up above. So it's kind of an extensive looking function when we have it all together. But we really just want to check with our test values. Do we get positive or do we get negative when plugging in the numbers for x? Now if we plug in negative 2, I'm just going to go ahead and let you all know kind of what happens here. If we plug in negative 2, it's going to look like negative 4, negative 3 times negative 2 squared, minus 1, divided by a lot of stuff, negative 2 squared minus 1 raised to the third power. We just have to be real careful about this. If we plug this number in, we're actually going to get a positive out as a result. And it will tell us that it's concave up. Now if we plug in 0, for our x, it's going to now come out to be a negative number. We'll have concave downward. And then lastly, if we plug in 2, we just have to calculate it out, which in this case is now going to be back to a positive again, concave up. Now one thing we may think about are these two numbers here. In the past, we were calling these inflection points, right? Because that's where it changes from concave one way to the other. However, these are not in the domain. So from the very beginning, we had talked about how x, negative 1 and positive 1 are not included in the domain. So these are actually not inflection points. So we don't even have to worry about those numbers in. They do change in concavity across those numbers, but because they're not in the domain, there's actually not a point there for an inflection point. So now we're ready to try our best to set up and graph this thing. Lots of stuff to do, but now we can just kind of summarize it and I'll put it together in a picture. So we had our asymptotes. We had figured out we had a horizontal asymptote at y equals 2. Okay. We had a vertical asymptotes. We actually had two of those for negative 1 and positive 1. Okay, so that's our two vertical asymptotes, x equals 1, x equals negative 1. Okay, and then we look at the information about concavity and all that stuff. Notice we also had x and y intercept at 0, and that's also our local maximum as well. So this thing was increasing from negative infinity to 0. It's concave up. So what I'm going to do is draw it here really close to this asymptote and concave up and increasing like so. Now it starts going, still increasing, but turns to concave down at -1. So in between here, I'm going to start drawing it concave down, but now close to this asymptote. And then here, it's going to change and start going decreasing, but also still concave down. And then over on this side, it's decreasing and concave up. So it's going to kind of cup upward, but also be decreasing at the same time.